All right, for section 8.3, we're going to do a different trigonometric integration. We're going to use trig function substitution here. And what we do is it's all based off of right triangles when you see radicals inside of integrals. So if you see a square root of a squared minus x squared, to me that's the Pythagorean theorem. This is the hypotenuse, this is the leg, um, this whole square root represents the other leg. If I have a squared plus x squared, this square root of all that represents the distance of the hypotenuse. And then if we have x squared minus a squared, now the x squared's on the hypotenuse, a is one leg, and the square root of all this represents the other leg. So again, reviewing your Pythagorean identities, we're going to need cosine squared theta is 1 minus sine squared theta, sine squared theta is 1 minus cosine squared theta, secant squared theta is 1 plus tangent squared theta, and tangent squared theta is secant squared theta minus 1. All right, so looking at this first radical here, the square root of a squared minus x squared. As I said, a squared minus, and whenever there's a minus in there, the first term, the square root of that a squared, that's your hypotenuse. Now, x is going to be one of my legs, and so is going to be the square root of all this. But we always want the simplest x, if possible, across from theta. So that puts this square root on the bottom for this leg. And we always want your trig function to be x over a. So in this case, opposite of theta is x over hypotenuse, that's sine theta. Solve for solve for x, multiply over the a. There's my equation solved for x. All right, for our second radical, okay, now the a squared plus x squared, that's your hypotenuse. And again, a and x are your legs, but we want to have x to be opposite the theta. Again, remember, we always want a variable expression opposite of theta. So x over a, this is opposite over adjacent with respect to theta, that's tangent of theta. Solve for x, a times tangent theta. Our next one was x squared minus a squared inside of our square root, that's a leg. So here, we're forced to put x on the hypotenuse. So now you have to put this square root of x squared minus a squared across from theta. Again, you want an x variable expression across from theta. We would like to be the easiest one, but in this case, with an x squared minus a squared, that's your hypotenuse, so that's got to go there no matter what. So now the leg is a, based off of this relationship. A is the adjacent, x is the hypotenuse, but we want x over a, so we're not looking at cosine, we're looking at its reciprocal, secant theta equals hypotenuse over adjacent, multiply over the a, there's my answer for x, or my solved for x equation. So the pattern in how we're going to do this is your integral will have algebra in it, ugly square roots in it. We're going to convert it to trig, simplify everything to a very easy trig integral, integrate it, and then based off of your right triangles you've created, use your trig functions to create the ratios to rewrite it in algebra format. So again, the steps: 1, draw the triangle and label the sides. You need the triangles when you have to rewrite it back into algebra. You got to base it off of this triangle. Number 2, choose your simplest trig function. Again, we're always looking for x over a. That's your goal. Solve for x, and once you find x, you're going to take the derivative of both sides. We're going to substitute in the x and the dx into our integral. We're going to simplify using trig identities, integrate a simple trig integral, and then replace all your trig functions of theta with x values based on the triangles that you created. So for example, I'm integrating 1 over the square root of 25 plus x squared. Okay, with the plus sign, that is my hypotenuse. Now, you always want to have an x across from theta, so the square root of x squared is x, square root of 25, 5. Opposite over adjacent, that's my x over 5 fraction I want to create. That's tangent theta. Solve for x, just multiply the 5 over. There's x. Now take the derivative of both sides. So dx is equal to 5 times secant squared theta d theta. Step 4, substitute in. Okay, notice I took my dx, multiplied it to the 1 on the top. So if this was a 5 or a 3, factored to the front, so it's a 1, so you can multiply your dx to the top. So 5 secant squared theta is going on in the numerator. And this x, I'm putting 5 tangent theta, and I'm going to square it. Now, a good rule of thumb is you want to manipulate the square root. So off to the side, I'm going to start to manipulate it. I cannot take the square root of 25 and the 25 tangent squared theta because of that plus sign. I have to get this plus sign inside parentheses. I'm going to factor out 25 as the GCF. That's 25 times this factor. Oh wait, that's a Pythagorean identity. 1 plus tangent squared theta, secant squared theta. Now that everything's being multiplied together, I can take the square root of 25, 5. Square root of secant squared theta, secant theta. That entire ugly square root simplified to 5 secant theta. Substitute it back. Wait a minute. What are my 5's going to do? They're going to cancel. What's this secant theta going to cancel with that one? That ugly integral is now just secant theta d theta. Well, if I integrate that, that's the natural log of secant theta plus tangent theta plus a constant. Now I put a subscript 1 there because a lot of times when you do this trig substitution, you're going to create another constant to add or subtract to this. So to finish this off, we have to bring it back to algebra for number 6. Secant theta, that's hypotenuse over adjacent. Tangent of theta, that's opposite over adjacent. I already have it right there, x over 5, so I substitute them in. They have common denominators, add them together. Now, here's where you got to remember some old algebra. When you divide inside the argument of your natural log, inside these absolute value bars is your argument. You can use the quotient rule of logs. That says you can take the natural log of the numerator. Okay, so the natural log of the absolute value of the square root of 25 plus x squared plus x minus the natural log of whatever factor you have in the denominator, which is 5. So the natural log of 5, or absolute value 5, it's still a 5. That's a constant value that you add to this proposed constant to create a brand new c. So my final answer is the natural log of the absolute value of square root of 25 plus x squared plus x with a plus c outside my absolute value bars. Example 2. All right, now it's 1 over x squared minus 25. X squared minus 25, that x squared, that's my hypotenuse. All right, so opposite of theta, you have to have some kind of variable x in it, but I already used the easy x, so I got to put the ugly square root over here. 5 will be the adjacent side. So to keep this as x over 5, hypotenuse over adjacent is secant theta. Multiply the 5 to secant theta, that's my x. And now take the derivative of that. dx equals 5 secant theta tangent theta d theta. Make the substitutions. We'll put dx on the top, 5 secant theta tangent theta d theta. Put in our 5 secant theta for x. Simplify the square root. That's 25 secant squared theta minus 25. Factor out the 25. Secant squared theta becomes tangent squared theta. We can take the square root of both to get 5 tangent theta, replace the denominator with 5 tangent theta, cancel the 5, cancel the tangents. Oh, look, same answer as before. Integrate secant theta d theta is the natural log of the absolute value of secant theta plus tangent theta plus that constant 1. Well, we already have secant theta, that's x over 5. Tangent of theta, that's opposite over adjacent. Add the two fractions, they have the common denominator, and again, use that quotient rule to bring out the minus natural log of the absolute value of 5, which again becomes one big constant. So my final answer is the natural log of the absolute value of x plus the square root of x squared minus 25 with a plus c. Example 3, here's my square root up in the numerator, but now they gave me some more x stuff on the bottom. That's okay. It's just going to take a little more work to simplify. So since it's 4x squared plus 9, this whole radical, that's my hypotenuse. All right, take the square root of 4x squared, that's 2x. Put that opposite of theta. The square root of 9 is 3. Put that as adjacent. So here is my x over my constant. So 2x over 3, that's tangent theta. Solve it for x. Multiply 3/2 to both sides. Take the derivative of both sides. Dx equals 3/2 secant squared theta d theta. Now we're ready to substitute in. So my dx, I'm going to leave that off to the side because I have something other than a 1 here. But I'm going to have 4 times 3/2 tangent theta squared plus 9 all over 3/2 tangent theta to the 4th power times 3/2 secant squared theta d theta. So it's going to look a little messy, but then we're going to clean things up. Let's square this. That's going to make it 9/4 tangent squared theta. We're going to simplify the radical now because the 4's will cancel. We can factor out a 9. Tangent squared theta plus 1 becomes secant squared theta. Square root of 9 is 3. Square root of secant squared is secant theta. Replace that in the numerator. In the denominator, I took 3/2 to the 4th power. So 3 to the 4th is 81. 2 to the 4th is 16. The reason I want to raise that to the power is because I want to take all these scalar factors to the front. So 3 times 3/2, that's 9/2. 81 over 16, that's what I'm dividing by, this fraction, but we don't divide by fractions, we multiply by its reciprocal. So secant theta times secant squared theta, secant cubed theta, all over tangent theta to the 4th power d theta. Now, again, you need even powers on secants, odds on tangents, so this is everything to sines and cosines. So let's simplify our fractions. That's going to be 8/9. My secant cubed theta, cosine is 1 over cosine cubed theta. 1 over tangent theta to the 4th power is cotangent theta if I move it up to the top by the reciprocal identity. And cotangent is cosine over sine. Now we can cancel. So I get cosine theta over sine to the 4th theta. And so I need a little more room, so I'm going to take this to the next slide. So here I have cosine is to an odd power. Move that with your d theta. And then sine theta will be your u. The derivative of sine theta is cosine theta. So this becomes 1 over u to the 4th. Just move the cosine theta, d theta together. Leave a 1 up there. Now that's going to be u to the negative 4th power. Add a 1 makes it u to the negative 3rd. Divide by negative 3. Multiply it as a fraction. And that's going to give me negative 8 over 27 u cubed. Because now that negative power, I'm going to move it down into the denominator with a positive power. Bring back my sine theta in the denominator, but I don't like this denominator to have a trig function in it. Think of this as 1 over sine theta, which is cosecant theta. That way I have no trig functions now left in the denominator. We have its reciprocal identity. So negative 8 over 27 cosecant theta cubed plus c. You would think after all that work you're done. We're not. We have to turn this back into algebra. We got to get to step 6. So based on my right triangle, okay, cosecant is the reciprocal of sine. So instead of opposite over hypotenuse, it's hypotenuse over the opposite. So substituting in the square root of 4x squared plus 9 over 2x, I am not going to cube a square root. If that was a cube root, I would cube it. So we'll just leave the top alone, but I am going to cube the bottom to make that an 8x. So that 8 cancels that 8. So now I have that square root of 4x squared plus 9 cubed all over 27x cubed. Again, we cubed the 2x. Don't forget your negative, and don't forget your plus c. All right, example 4. We're looking at integrating the square root of 9 minus 25x squared. So that forces the 9 to be your hypotenuse. So the square root of 9 is 3. The square root of 25x squared is 5x. We want to put that across from theta. That's a nicer x expression than this one. So this square root's the adjacent side. So here I have opposite over hypotenuse, that's sine. Solve it for x, multiply 3/5 to the sine. Take its derivative, dx equals 3/5 cosine theta d theta. Substitute it into the square root. So 3/5 sine theta goes right here for the x squared. Dx is 3/5 cosine theta d theta. Take the ugly square root, take it to the side, and simplify it. So squaring 3/5, that's now 9/25, which means those 25s cancel out. I factor out the 9. I'm left with 1 minus sine squared theta, which turns into cosine squared theta. And now, because I have 2 factors inside my square root that are perfect squares, I can take the square root of 9 and the square root of cosine squared theta to get 3 cosine theta. Put that back here where the square root was. All right, multiply the scalars. 3 times 3/5 is 9/5. Cosine theta times, oh no, that's cosine squared theta. I need my half angle identity. So substituting in 1/2 times 1 plus cosine theta d theta, take the 1/2, multiply it to 9/5 makes it 9/10. Integrating 1 with respect to d theta, that becomes a theta. Integrating cosine of 2 theta is sine 2 theta, but then again, don't forget to take the derivative of the inside argument of 2 and divide that into sine 2 theta or multiply it by 1/2. Now, we're not done. Okay? Because we're in theta, we really don't want to have a double angle here, so one thing you can do is use the double angle identity for sine. Sine of 2x is 2 times sine x cosine x. So I substituted that in. Then we're going to do some simplifying. The 2 can go into the 20 10 times. Now, that's a lot of work so far. Again, we're not done. We still haven't done the last step of 6. We got to turn this back into algebra. So sine theta, cosine theta. Look at my triangle. Sine theta is 5x over 3. Cosine is the square root of 9 minus 25x squared over 3. But theta, good question. What am I going to do with this? To solve for theta, go back to step 2. We're going to solve this. Now, to get theta by itself, you just do the inverse sign of both sides. There's theta. So we're going to take inverse of sine of 5x over 3 and multiply it to that 9/10. Over here, we can do some simplifying. 9 on the top, 3 times 3 is 9, that will cancel. 5 goes into the 10 twice, so that gives me x times the square root of 9 minus 25x squared, all over 2.